Good afternoon. So this is week number 5, lecture B. Can you hear me? Okay. So I ask you to review the slides regarding all different types of signals. I ask you to review the slides about basic circuits using Laplace transform to solve circuits problem. Have you already reviewed those? So here is the meeting plan for week 5. Okay? So week 5, we are going to continue about signals and systems and controls. Okay? So this part will be the central theme of the next 2 weeks plus this week. So I assume that you are going to be very familiar with Laplace transform, okay? Laplace transform. And you know partial fraction expansion, you know initial value theorem and final value theorem, and be a friend of delta and the unit impulse, okay? And the transfer functions and impulse responses. So you can see we are going from circuits to signals to systems. So this is a needed level of abstraction that can give you the more systematic way to deal with mechatronic systems. Okay? So that's why we need to learn that. Did I tell you more than once that between a technician and an engineer, where you draw the line? Laplace transform. Okay, and signal systems. And you talk about transfer functions, poles and zeros, so on and so forth. So this deck of slides, I'm not going to go through all those details with you. Okay, so I assume you are going to read it. Okay, so we are going to do is continuous time signals and systems. So it will be the main theme for this week and next week. Okay. Remember, for mechatronic system today, majority of them are controlled by computers. So in fact, they should be digital controlled. So therefore, it's a discrete time. So discrete time. But we're talking about continuous time. Why? Because this is the real mathematical foundation. Only you have the foundation in continuous time, you can do the job in discrete time. Okay? So we're talking about signals and systems. So we said there's a system in here, you have signal in here, and you have signal in here. Okay? So you pass a signal to a system, you get another signal. Is that right? So it's a mapping between two signals. On the other hand, okay? So this is a U of t, this is Y of t, this is the transfer function G of s. So if I give you an impulse delta of t in here, what I'm going to get is something called G of t. G of t has a name, it's called impulse response function. Impulse response function. Response function. So I was trying to confuse you last time that, so GT is a signal. This signal actually can be used to completely characterize, tell the stories of the whole system here. Why? The reason is, for any output with any input, okay, U, not necessarily impulse anymore, and this is simply convolute with G of t, okay? And by convolution, the definition is 0 to t, and you have U detail. Okay, so that's called convolution. Okay, that's called convolution. Can you guys see it? Oh no, can't do this. Can you see it? So it's convolution. According to Laplace transform, then so there's a UT and a US Laplace transformation pair, YT and Y of S is Laplace transformation pair. So I know that my output Y of S equals input U of S simply times the G of S. G of S is called transfer function, and G of S in here is nothing but the Laplace transform of the G of T. Okay? G of T. So all these are kind of connected. I hope you understand that. So our starting point is linear, continuous time invariant. So the constants are just a constant, not time varying. So these are constants. So I told you the story about Heaviside, okay? He's the guy who simply replaced the ddt with rho as an operator. So he even can talk about square root of rho, okay? Rho. And so then by doing this, is a precursor of Laplace transform. And just last lecture, I told you how important to talk about zero minus. If you forget zero minus, you will be in trouble. Your results could be wrong, okay? So because otherwise you cannot handle the situation like a capacitor previously charged, okay? Then you switch, that pre-charged one is kind of initial condition. So for derivative y and capital Y of S, then this is what they call derivative property or derivative law. So we usually use Laplace transform like this, okay? Again, I'm going to give you the table of like this when we do exam, okay? Close book exam. And I'll probably will also attach one of this for you. It's called the summary of all the properties. Okay, properties. So with that, with all the initial conditions can be considered as 0, x0 is 0. Then you end up with a relationship like this one. So U is input, Y is output, G is called Laplace transform. Transfer function, okay, transfer function. And this transfer function usually is written in terms of B polynomial, A polynomial. And in the denominator A polynomial, the highest term here is normalized to 1. This polynomial is called monic, okay? Monic, so this is monic polynomial. Then of course B cannot, okay? If we put B also monic, something is wrong. Something is not so right. Okay, so in state space format, if x dot you do a Laplace transform, you are going to have sxs minus x0, so you end up with something like that. So in other words, x, you don't see x in here. You don't see the x in here. So x is something called internal. So usually. So when you see x, so u is called input, right? Y is called what? Output. What is x? X is called state. The reason I want to tell you that, in fact, we should say something like this is called internal state. Internal state. X is your internal state. Because you don't see from outside, okay? And we reviewed last time first order plus delay, FOPDD. So this is pure delay, and this is a heating system. And And for the temperature system, then you get transfer function. This transfer function has a special name. It's called FOPDT. If I ask you to spell this one for me, now you can, right? First order plus delay time. Okay? So why we need to care about this single out this format, okay? It's because 80% of more than 80% of all control tasks in the world are for thermal temperature control. And those thermal control can be approximately modeled by this FOPDT. Okay? So we're repeating, don't worry. And we're talking about stability of transfer functions. So we're talking about impulse response. We understand what is the impulse is to make sure my delta of tau, d tau, minus infinity plus infinity, this one will be 1, okay? This one will be 1. That's called delta function. And there's another one, it's called only when delta tau is 0 when tau is not 0, okay? We know that. So these two should be combined to define the delta. So, okay? At the 0, when tau is not 0, then delta tau is 0, okay? But what is delta 0? Is this infinity? Can we say that? I don't think so. I don't think so. So, but graphically speaking, it's something like this. So you have an impulse with 0 duration and infinite magnitude. Okay. But the question is, you cannot say 0 times infinity is 1, right? Okay? You can say that, like what we are showing here. We always need to have something like this. So that analogy is questionable, okay? In other words, don't try to tell people you know, or Dr. Chen told you this. No, I don't think so. I don't like that. Code is wrong. Are you implying 0 times infinity is 1? No, don't do that. It's not defined. So that's why this is called generalized function. Generalized function. So it's not defined by its own, it's combined properties. Together they define what is delta T. Make sense? Don't tell people I said this is true. No, this is not. This is not. Okay? Don't think that way. Okay, so excuse me. I need a coffee. Okay. So when I send, so this is what we call final value theorem. Did you see anything wrong here? This should be 0, okay? You send S to 0. And under the input is step, I ask you to derive, last quiz, what is the Laplace transform of a step function according to the definition. I saw at least 5 or maybe 10 of you didn't do it correctly. Please fix it, okay? So find out why you need the step corresponding to 1 over S, okay? And cancel this S, send S to 0 is G0, okay? So this G0 has a special name, we tell you more than once. It's called DC gain, okay, DC gain. For the system, you have a system will respond. Then this side is very odd. Basically, my set point is here. I want you to be here, but initially it goes opposite direction. Okay? Why we have that? It is because of non-minimum phase zero behavior. Okay? Non-minimum phase behavior. Okay? I'm going to show you an example, but before that, relative degree. Okay? Relative degree is the denominator degree minus numerator's degree. Okay? Like the last time the quiz, the answer is 0. And still many of you didn't tell me that's 0. What's wrong with you? Okay? I'm not very happy about it. I even said you put a 0 here, and you still put something not 0. Okay. Don't tell me who you are, I already have a record. Okay. Pose zeros. Okay, so you have a system that is first order, then this is the first order. What is a k over tau s plus 1. You add an input in here. What is my input? I do a step. Basically, input is like 1 of s. So therefore, what is my y of s? Is input times g of s. It was a function, so the 1 of s times tau s plus 1 and the k. Okay? Then this is a product form. This is the product form. So how I can come out of this coefficient? You can try and error, you do your own trick. Fine, you can check. Then this pans out. This is just k left. So yeah, this is the same. To bring this product form into a summation form is called partial fraction expansion. Do you know that? How to do it? Okay. I'll teach you copy in a moment. Okay. So then you use lookup table. You put it here. You look up table, put it here, so you get k, you can pull out the k in front, the 1 minus e. Is this the correct answer? If you write like this, I will say it's wrong. Don't do that. You should put a comma and t greater than equals to 0, okay? Because otherwise, you imply t can be anything, right? So remember that, okay? Remember that. So then if you have a complex conjugate, like a second order system, so then you can write down analytic form. So this one is called canonic second order system. Okay? For the first order, we have k over tau of tau s plus 1. But for second order system, you have 2 parameters. One is called omega n, another one is called damping ratio. Okay? So this phi is damping ratio. If the phi is 0, okay, then this will be complex conjugate, okay, on the imaginary axis. If the phi is 1, okay, then you have a complete square in here. Then that means you have omega minus omega n is your root. That has a multiplicity of 2, okay, multiplicity of 2. So there are multiple cases. Let me show you the possibilities. So let's say you have a root in here. Okay, this is the real part, this is the imaginary part. So I said that there are many cases. The first case is when it's here, okay? It's here. When phi is 0, okay? So when it's phi is 0. Or you can say, oh, could be all here and here. So they are all here and here. So they can all even here, okay? So they can be multiplicity of 2, means s plus omega n squared. Omega n squared. You may wonder why we need to have omega n squared here. Why? if we put 0 in here, this is 0, this is also 0, then this divided by this is 1, okay? So the DC gain is 1. That's a kind of normalization. DC gain is 1. So that's why you should not put 1 in here, you put omega n square in here to make the DC gain. So this format is called canonic second order model. That's the used canonic. Then because of that, if you have a step, then you will be able to write in terms of analytical format like that. So in the end, you can write y of t is sort of, so it could be like this, depending on where your poles are located. So this is a complex conjugate, okay? Complex conjugate. So you have oscillation and damping, okay? So the reason you have oscillation is because you have a complex conjugate. The reason you have damping, get out damping, is because you are living on this side. But if you live on this side, this damping is not possible. It's not damping. It's going to like blow up. Okay. So we are going to see zeros. Okay, zeros. This is the part ignored by a lot of people in the beginning. So I'm going to show you something here about simulation here. So take a look at this picture. Again, what is the DC gain here? 1. Okay. In other words, if I give you a step response, then what is? I give you a step. After transient, you will settle. So that means if I give you a step as an input, what is the output? What's the output when the output settles? Why t goes, this is t goes to infinity. It will settle to G0, right? DC gain, so DC gain is 1. So you give a step 1 input, you're gonna have something also, step go to 1, okay, eventually. But there are found different ways to go to, so this is called transient, okay, transient. But usually when you have a system, you give a step, then the system will respond, okay? So it's called a reaction to this, reaction curve, okay? But I don't like it, so I give you a step, you are going opposite way, then come back again, okay? That's called undershoot. That's called because of this pole. Nothing to do with the pole. It's only to do with the 0. When the 0 is on the right half plane. So when C is 0.1, let's go back and see. C is 0.1. What is the 0? 0 is 0.1, okay? 0 is 0.1. So it's on the right half plane. So when 0 is in the right half plane, you are going to have this opposite way. So instead of chasing the input, you can offset, then you chase, okay? That behavior is called non-minimum phase behavior, NMP. So when this 0, S is C, when C greater than 0 is a non-minimum phase 0. It's on the right half plane. So these are equivalent. On the right half plane 0 is a non-minimum phase 0. Okay? Make sense? If in the future you cannot answer the question about what's the definition of non-minimum phase 0, he said, I never heard about it. Then there's only one explanation: you missed the class. I told you multiple times, when the 0 lives on this side, not this side, this side. If we live in here, that's called non-minimum phase 0. Okay? Now I'm going to do to you that if you poles living here, then the system will be unstable. Okay? Unstable. So I think these are very simple things, and but from mathematical point of view, is the transfer function is a Laplace transformation of its impulse response. Okay, if you for any zero such that real part is less than, then you have this one all limited by this, which is so true. Okay, it is so true. So this is the zeros on the step response. Okay, put the zeros on the step response. And the non-minimum phase zero is an undershoot, is a problem ignored by a lot of people. Okay? So my students in my class must know this. Okay? Must know this. NMP, non-minimum phase zero. Okay? So and there's a way to estimate what is the size of the undershoot. Okay? So you don't have to memorize this. Just you know that if you have a right half plane, you can write down RHP 0. You have RHP 0. Then this 0 is called non-minimum phase 0, and this non-minimum phase 0 will cause undershoot. Okay. Okay. So if you want to have a very fast response, then you have to have a very big undershoot. So that's the problem. Okay, so let me skip these two because if you have a zero, what do we mean slow zero, fast zero? That's how far away from the imaginary axis. Okay, imaginary axis. DC gain is 1, we'll assume we have a DC gain that is 1. So when S is 0, G is 1. Then when you have S is C, that is 0. Okay, that is 0. If the 0 is on the left half plane, this C less than 0 is this side. Then your 1 minus YT is the unit step response. And that is the arrow. That is the arrow. 1 minus YT. Okay, 1 over YT. So the zeros and the dominant pole related by this. So this is poles is bigger than the 0. So then make this only less than 1. So then you can draw a conclusion about what is your maximum overshoot, and what's the area to be bounded by this. Okay, can be bounded by that. So these are kind of qualitative behavior of this non-minimum phase thing, and it probably is too advanced for you to derive, but you just know there are some qualitative and quantitative relationship here. Okay, so today, what we are going to do is more on frequency response. So you have a system, you put a time function, you get another time function. Yes, that's great. So this is called time domain response. There's another thing called frequency domain response. Okay, frequency domain response. But before we do that, let's look at today's quiz. So basically we are talking about the delay, okay? Talk about delay. So basically you have a step, okay? And you need to understand when the step was delayed with time b, then what is Laplace transform for that. On the other hand, you have a pulse like that, can be written as two-step minus, then you get what's left. It's called a gate. It's called a gate. Okay? It's called gate function. Okay? Gate function. So please spend some time going through that, setting up this frequency response for everybody. Okay? Everybody. So frequency response. Okay, frequency response. Before I do that, I want to show you something a lot of people will make mistake. Okay? I want you to tell me what is the sine t Laplace transformation? Right? Okay? If you don't feel comfortable, we can go back and check the table here. Sine 1t is 1 divided by s squared plus 1. Okay? What if it's cosine? Cosine, you have an s in here. Okay? S in here. Okay? Now, wake up and look at this carefully. So what is the pole in here? You have a j and minus j, right? So this is a pair of complex conjugate on imaginary axis, right? Yes, great. Now you learn that I want to check. When t goes to infinity, I'm going to check what I should do. I send s to 0, right? And I have s times Laplace transform. Copy this guy here is s squared plus 1 is what? Yes? This looks right. However, are you saying that this one equals sine infinity? Obviously, it's wrong. Because when you go to infinity, you don't have an exact number. Okay, so this is not right. And that means this is not right. So, in other words, final value theorem here failed. You cannot do that, okay? You cannot do that. Okay? You cannot do that. You should be reminded that if you want to do g of s, then you send s to 0 is g function of infinity. To apply this as final value theorem, you actually need to check if all the poles of this guy, all the poles will be living in left half plane. Living in left half plane. So if not in the left half plane, you cannot do it. You cannot be on the imaginary axis. So that's why this one failed. There's a consequence of this failure here. Okay? There's a consequence of this failure. Do you know that? That means I have a system here, g of s, okay? Okay? And this system has sine t here, okay? I give you sinusoid with different omega. We'll just say a fixed omega here. So after long time, okay, after a long time, after all the transients are gone, okay? What is my ys? So, of course you can write ys is s squared plus omega 0 squared. And so according to here, I should put omega 0 in here. Okay, so that doesn't matter. So y of s is the input of s times g of s, which is correct. This is nothing wrong. This is nothing wrong. But I want you to write me what is yt. What is yt? Okay, and t is already a long time, like almost infinity. Okay, so very, very big T. Okay, then when everything's settled, how you write down this one? So I ask a student, a student to tell me when T goes to infinity, what is the yt? And people start to use final value theorem for me, and it turns out it's 0. It's wrong. Okay. Okay, it's wrong. Don't do that. It's not applicable because of that. It's not applicable. So what you really should think is, you give me a sinusoid going through linear system after a long time, then this thing is still sinusoid. It is still omega t, okay? But it has a different phase. It has different amplitude. And the amplitude is a function of omega. Phase is also a function of omega. That's the right way to think about frequency response. Okay? So we call this 8 omega and 5 omega are frequency responses. Magnitude and phase. Make sense? Never think about y infinity. You do y infinity this way, it will be wrong, okay? You cannot use, so it doesn't make sense. Never think that direction. So only think about, give me sign in, I have sign out. With same frequency, but different amplitude and phase. Make sense? So here is the statement. So you have g of s, can be written in terms of a polynomial, okay, a polynomial, numerator and denominator. Do you think the denominator has something in special? Yes. The highest order term has a coefficient of 1, so the whole thing is called monic. If you, in the end, you don't know what is monic polynomial, you will be in trouble, okay? So it's a monic polynomial, okay? So when I pass a sine omega, into this one, I also sine omega t into this one after a while when the transients are gone. So then my output will be also a sine omega, okay, sine omega, but with a different phase, with a different amplitude. The phase and amplitude, they may be different, and they are function of your omega, okay? So then I draw x-axis as omega, y-axis as phi, or y-axis as magnitude here. So that is called frequency response. Frequency response. So, and interestingly, the frequency response, you put j omega replacing here, you are going to have this exact complex. This is a complex number, right? Put j omega in here. So then this is magnitude and phase, magnetic phase angle format. So frequency response, okay? So something different you haven't learned before is instead of seeing a system respond to my step, also the react. That's called time domain response. This is called frequency domain response, okay? Your x-axis is not time t. Your x-axis is omega, is your frequency, okay? So in summary, okay? So a sine wave input force, input into a linear system, Hs, forces of sine wave at the output with the same frequency. So you can simply say sine in, sine out, okay? It's good, but this is only true when the system here is linear time invariant. Okay? Linear time invariant. This is only true for that. If it is not, you cannot say that. Say for example, I have a non-linear system. It is non-linear, not linear, non-linear. Then what's going to happen? So you think about here, you have, think about Fourier series expansion. You expand to frequencies of multiples of omega, of infinitely many, okay? If it is non-linear, and expand it into Fourier series, okay? That non-linear part we're not going to do it. But you know there are ways to do that. It's called describing function approach. Still we can use a similar idea. So I said frequency response. But you probably heard about something called Bode diagram. Bode diagram. So Bode diagram actually you have two plots. One is for the magnitude, okay? One is for the phase. So usually your x-axis in the frequency variable is used as a log 10 base, okay? Log 10 base. So the distance between any specific omega 1, and then you multiply by 10. So these two frequencies are called a decade away. The distance between them is called a decade, 10 times a decade. Okay, so basically they use a log 10. So this is log 10, okay? This natural log is Ln, okay? And so that's magnitude of frequency response is measured in dB. So the magnitude is dB. So we should use log 10 magnitude. So this is dB. So I already explained to you why it is 20. Where the 2 is from. Okay? Do you still remember? The dB originally was invented to simplify the cascaded amplifiers. Okay? So turn it into product of the multiplication of the gain into a summation. Okay, summation. So here we do log 10. But at that time, we measure log is between the signal's power to signal's power ratio. This power ratio. Or power is proportional to the square of the signal's amplitude or current. Square. So then you square, then you do log, square of 2 will be here. So this is basically the transfer function is a ratio between input and output magnitude. Magnitude, not power. Not power. Therefore, magnitude square will be the power ratio. So this is that why you have 20. I hope that's clear, okay? That's clear. The angle usually is in degrees or radians in a linear scale. Y-axis is linear scale for angle. We are going to work some basic things. So I think it's better we go through one by one. So typical one is you have a constant K, okay? You have constant K, okay? Constant K. So then this is also a constant, okay? Magnitude. Phase will be 0, okay? Phase will be 0, okay? So then your dB is simply 20 log, okay? 20 log. You put things up and down, it's like floating things up and down. So S to the power of K is a magnitude, a straight line, okay? With a slope, okay? Straight line with slope. 20 dB per decade when K is 1, and K2 is 40 dB per decade going up. So this is like differentiation. S is like ddt, differentiation, and differentiation is going up. 20 dB per decade. Constant phase is 90 degrees for K is 1, okay? Or K is 2, then K times 2 pi. So of course you will cross the line at 0 dB at omega is 1. Okay, J omega. So that's that case. So these are just the words, it's not very visual. I want to make it more visual. So let's go through an example, okay? Go through an example. So how we can plot a Bode plot of this one? Okay. How we do that? So you need to put this thing into what we call canonic form. Okay, canonic form. What this is the original form. This is the form of this. What we did for this. We did here is always 1 and divided by 10, S divided by 10 is 1, S divided by 8 is this, S divided by 4 is like this. So 4, 8, 10, and divided this one, you got 2, this is 1. So this format is the canonic format, okay, canonic format. Canonic format. We probably need to work on this next time, but this time we're going to just to show you that we can do a very simple approximation. So this approximation, this is the real Bode plot. This is approximated Bode plot. So this is called asymptotes, asymptotic lines, asymptotic lines. So there are a set of rules we can go through to draw the Bode plots. And this is a technique I want to elaborate with you next time. Okay, next time. But today we are going to talk about filtering a little bit. So this is a typical Bode plot. See, this is frequency, and this is a log format, this is dB, this is dB, so something like that. Okay. So for the filtering, so I hope we have seen this before. We have a pass band, stop band, and transition band. So the cutoff, when I say I'm going to cut off at some point, it is because I'm having the power of the signal was reduced by 50%. Well, power is square root of the amplitude. So the amplitude actually is square root of 2. Square root of 2. So H0 is a low pass filter and band reject filter. H infinity is for high pass filter. So this one can be drawn like this one. Okay, like this one. Okay. here is high pass, okay? Here is low pass, okay? And in between here, so this is called band pass, okay? Band pass. So these are the bands. And do you read what is the number in here? I told you last time. 0.707. 0.707. Okay, great. Excellent. So this is a typical focus response for band pass filter. So we are doing well. Let's go through very briefly about Fourier transformation today. So because I gave you a function of t, I want to convert this one fj omega. This is called Fourier transformation by f of t times e minus j omega t. So remember, Laplace transform, they use minus st, right? So s is j omega. Then this is the inverse Fourier transformation. But remember, I have to say something here. I'm very confident, at least one of you, okay, still do not know how to do what is the square root of minus 1 to the power of square root of minus 1? I'm pretty sure one of you cannot do it. I have a record here. So let me work for you, okay? So I know that the E, J, omega t, or omega, okay, is cosine omega plus J sine omega. So this is called Euler's formula. So therefore, I set omega is pi and a half. I'm going to have 1 plus 0 is E J pi. E J pi divided by 2. Okay? So in other words, I can write J equals this one, right? Okay? So in other words, I can write J to the power of J is this J replaced by EJ pi here and put a J in here. So this will give you E and J squared is minus 1 and so it's 1 divided by E pi divided by 2. Make sense? Yes? Tell me, do you really know it? Now, if you don't even know how to do complex numbers, how are you going to do frequency domain response? From day one, I told you you need to go back and review complex numbers, okay? And I told you I put this one to remind you on the quiz form, and you still don't write it correctly. It still tells me J to the power of J is I to the power of I. This is your answer. And it's more than one of you did this one to me. If I don't have a strong mind, I already died. Okay? Okay, I'm very serious. Are you learning? I'm not trying to complain every lecture, okay? I'm recording actually. I'll put on the YouTube. Please wake up and put your complex numbers. If you don't even know how to do complex numbers, how can you do frequency domain response? How can you draw Bode plot? I don't want to do Bode plot today with you. I know you're not ready. Over this weekend, go back and pick up the complex numbers, please. go and check your quizzes. So you just made me mad. So I just want to tell you that whenever you see this one, you should say, oh, I got a cosine omega t and sine omega t. Basically, it's a complex cosine sine, it's just like waves, okay? And you sweep to the omega, then you got, oh, yeah, that makes sense, okay? So then I'm going to have some of the fundamental Fourier transformation table. One is 2 pi delta, delta is this, mu is like this. This is gate, is something like this. Okay. This one is something about a second question in your table. Second question in your table. Okay. So this looks familiar. This is called heavy side step. Okay. Anyway, and they have properties similar to like you have linearity, of derivative law. So you do derivative in here, then it's j omega, j omega, Okay. But this is beautiful. This is beautiful. It's called Parseval theorem. Parseval theorem. So I want you to memorize that. So basically, you have a signal, okay? Okay, you have a, say for example, you have a f squared. This is the same as f. Then you can put this together and so in other words, time domain energy together. Think about energy, okay? Your signal square is like energy, right? So, but this is more general than energy, okay? I'm just using energy to help you to understand. So in time domain, you saw the total square add together is the energy of the system, of the signal f of t. Okay? It's the same as you see you live in frequency domain. Okay? The energy didn't change, just in a different domain you see it. Do you get it? Okay, so this Parseval is beautiful, right? So it connects your frequency domain and time domain in such a nice way. What's next is to show you something very interesting. I love it. Okay? I love it. You can repeat it. We are going to go through it. So there was an old saying that a picture is worth 1,000 words. I think this picture probably deserves more, probably worth of 10,000 words. Why? So this visualized behavior, when you play with some of the parameters here, say for example, I have case to game, okay? So if I give the step response, okay, step response, this is a step response. So I give a step response, if I k is bigger, then of course my output is bigger, right? That makes sense. K is bigger than my, and the y infinity is big, because y is 0. Y infinity is G0, right? G0 is K, so when K goes up, these are the Y infinity, right? Did you forget? I said Y infinity is G0. We have derived it before, right? Good. But when you use the G0, you need to be careful about your pose should be on the left hand. It's not like sine. Sine you have to computate on the imaginary axis. That will not work. So if I do body plot, so it's like this is a frequency, this is a magnitude. So if you have K goes up, the magnitude goes up. Others, the corner frequency, this tau is the same. Tau is the same. Tau is the same. And when K is very small or big, it doesn't matter about the phase. The phase is the same. Phase didn't change. So up and down, the magnitude changes, but phase didn't change. Did you see it? Because its phase has nothing to do with K. It's only with tau. Okay? So that is for the first order system. Okay? First order system. But what if I have different tau? So for keep the K as the same, so Y infinity is the same, DC gain is K. K didn't change, K is the same, can you see? But if you reduce the tau, then the system will go faster to slower. So tau, if tau is bigger, then the system is slower. Okay? This tau actually is going down. Okay, going down. Okay, going down. You increase the tau, it becomes small. Or in other words, your tau will closer to the imaginary axis, minus tau, right? 1 over tau. Okay? What's the root? Root is 1 over tau, right? Minus 1 over tau, right? 1 over tau. So this is my pole here. Okay? If I increase the tau, what I'm going to get? This guy will move towards here. Okay? Closer to that. So in other words, the decaying is slower and slower. If the pole goes to here, then it will be damped away very quickly. Okay, so let's continue. So this is the canonic first order system. You have two parameters, gain and the time constant. Gain and time constant. If they change, it will behave like this. Okay? So in the future, if I want you to sketch the qualitative behavior of the system in time domain response and frequency domain response, as K and tau goes, do you know what's the trend? You should, okay? Visually, you show people. This is conceptually important. Now, let's switch to the second order canonic system. So again, the DC gain is 1. In other words, it will goes to 1 as it goes. Okay? But if you have sinusoid, it will never rest on anything. Okay? So when phi is 0, then it's a sinusoid. Okay? So when you decrease the phi, then it will become more and more oscillatory, okay? Until it's 0, okay? Until 0. So this one is when it is 0, okay? 0. All right. I think this mistake here should be omega n, okay? Omega n. So imagine that when phi is 0, we don't have this term. We have s squared and omega squared. What if my s is j omega? So then will be minus omega squared and plus omega n. So when omega is omega n, then there is something divided by 0 here. So then that magnitude will go to infinity. So this is called resonance peak. Okay, that's why we have resonance. And that's why omega has a name. It's called what? You should ask what does N stand for? Natural frequency. Yeah. Because this is the system. Naturally, if your excitation, if your frequency is this at this frequency, then they will be amplified infinitely. That explains a lot of YouTube movies show us London Bridge oscillation. People walk, then suddenly it is oscillate a lot, and then crash. And I think it's kind of resonance. That kind of event, you heard about it? What's the root cause? Root cause is because of this peak. Or another root cause is because of this is 0, and this is j omega. This is minus omega square and omega square. And this is the same, is 0. Okay? So in other words, those crashes is because of divided by 0 event. Okay? Divided by 0 event. So here, okay? And magnitude is from 0 and then transit to minus 180 degrees. 180 degrees. And of course, here you should ask, what's the slope in here? What's the slope in here? What's the slope in here? The slope is called minus 20 dB per decade. This is minus 40 dB per decade. When you change the tau, you can see the corner frequency will be different. And also here it's different, okay? And if omega n is different, then the peak point is different, can you see? It's different. It's very interesting. So this is nicely behaved. This is a nicely behaved system, a second order system. Think about this as a second order system when phi is 0 or omega is 1. So then you add A, when A is 0, then you don't have this one, right? So A increases, then you have 0 added on that. So you come initially like this, then this. When A is really big, you overshoot like that. So then your second order system will be like this. When A goes up, then you should also see when A goes up, the omega will be small. So we can predict this type of behavior. Okay, behavior. It's called lead and lag and lead. Whichever is first, depending on how big is your A, it will become the phase like that. Lead or lag and lead. Okay. So now, if we put A is kind of minus sign in here, so what's the difference between this and this? The only sign here is different, okay? So in other words, the pole, the 0 living on left half plane, like this, when A greater than 0, then this will be mirrored in the right half plane. So this is a kind of non-minimum phase 0. So you can see that step input as A goes up, then you can see that initially A small, then it should be like this, A big and A big. So this overshoot. So this is undershoot, this is overshoot. Okay? You see it? Okay. So this is pretty weird in practice because it's anti-intuition usually. So you get very clumsy and get panic about it. You thought the system would go this way, but actually go that way. Makes sense? So so don't feel strange because of, so you know, oh yeah, maybe there's a NMP, non-minimum phase 0, okay? NMP 0. But interestingly, I want you to look at this one and this one. What do you see? Yeah, identically the same. This is the same because the magnitude of this one is the same. Make sense? Okay, so but the phase is different. Can you see? So this is 0, they come down to here, but this one is minus half pi, but this one goes to 3 pi divided by 2. Okay, 3 pi divided by 2. Not minus, it's positive. Not minus, it's positive. This is positive. So what's wrong here? What's wrong here? So you can see the phase here is always starting from 0, but here is not starting from 0. It's starting from something big than 0. So that's called non-minimum phase. Non-minimum phase is because of that. Okay? Non-minimum phase. Now you understand? So I know in the beginning you have no clue why we say non-minimum phase. Because the magnitude are the same for these two cases, but the phase is different. Which one is bigger? This guy will give you larger phase. This guy will give you minimum. So it's called non-minimum phase. So therefore, the following things are equivalent. Okay? Non-minimum phase 0, right half plane 0 are the same. In some of the textbooks, people say unstable 0. I hate it. I don't like it. It is stupid. Because 0 will never affect stability. What do you mean unstable 0? They simply, the zeros living in this side or this side will have no effect about stability. Stability only counts about where your poles will be living. If your poles living in this side, then the system is stable. Your poles living this side, the poles are unstable. Okay? So, when you have a non-minimum phase 0 in here, so you say, oh, there's a 0 in the right half plane for RHP 0. RHP, that's fine. Never call it unstable 0. It's illogical, it's wrong, and Dr. Xiang hated it. Okay. So although people use this one quite a lot in textbooks and papers, if I hear that, I know he's not a real expert on that. Give me back your homework and not homework, I'm sorry, your quiz. The first one, the answer is 1 of s times e to the power of minus bs, right? And remember you have c, don't forget c divided by s. So the second one is gate, right? So you still do the same. Gate. The last one, you probably have some trouble. So I want you to think about it, okay? It is wrong to write minus. It should be plus. Did you get all your quizzes back? Okay. If you cannot do the third one, it's okay. So, you know that the second answer is c divided by s bracket 1 minus e minus bs, right? That's correct. But now you multiply this one with the sinus of it. So you only have half of the sign left. What's the impulse? So the answer is wrong in the last line. That's wrong. Don't do that. That's wrong. That's wrong. The correct answer is 1 plus. So you still have a w divided by square plus w the last line, the line that last, in your quiz, the last line is wrong. Okay? Is incorrect. Surprisingly, it's not right. I'll explain to you why next time. So the correct answer should be plus 1 plus e to the power of pi divided by omega. Please submit your quiz, and then we finish here, and have a good weekend. If I said something about the complex number, if you are uncomfortable, make yourself comfortable this weekend by learning complex numbers. Or next time, you should not miss my class, and it's about 4 o'clock. Okay?